Hi, I'm Tim Zacharias with Cougar USA and your host of Building Value. We are in Las Vegas, Nevada at the AHR Expo, 2022 Expo, here in the Grumfoss booth in the middle of the show. And I've got two guests with me, Pete Korzeniewski and Chris Ireland from Grumfoss. Welcome to the show, gentlemen.
Thank you. Thanks for having us.
Yeah. Awesome. Really excited about this episode. Always enjoy talking with both of y'all. But really what we're going to be talking about today is the evolution for Grumfoss moving from products to solutions and talking about how distributed pumping is a paradigm shift in closed-loop design. On Building Value, we go behind the scenes of building operations to showcase the people and products that make buildings work and the value they bring to the community. Pete, can you tell me a little bit about where you grew up?
Yes, I grew up in upstate New York, or central New York.
Yeah.
So where I live now is Syracuse, but where I spent most of my childhood was in the Finger Lakes, not too far from there.
Okay.
But
I have no idea what that is.
Yeah, it's we're far away. We're 4 hours from New York City.
Okay.
So it's cold and snowy, somewhat mountainous, lots of lakes and streams.
Nice.
It's nice.
Yeah, very nice.
If you like cold and snowy and not a lot of sunshine.
Yeah, that's a big contrast from Houston, Texas.
Yeah, a little different than Houston.
Bit different.
Yeah.
So, Chris, what about you?
So I was born and raised in Sacramento, California. And then
about as far away as you can get.
Yeah, yeah.
from
Pete,
yeah.
Which is good.
Yeah.
I prefer that. I think he does too.
Good to have a little distance.
That's hilarious.
So I lived there till I was 12, and then my family moved to Kansas City, Missouri.
Okay.
And so then I was in Kansas City from then on till I went to college.
Nice. Where'd you go to school?
Utah Valley University.
Okay.
Yeah.
And then how did you end up at Grumfoss?
So I was working with J.E. Dunn Construction in Kansas City. I was there for about 6 years doing project management.
Yeah.
And I was working on projects like the Federal Reserve, the Kauffman Center with a big concert hall and theater. And this opportunity with Grundfos came along, and it seemed like a really great opportunity to try something different and get into sales. And I made that change, and they've moved me to Phoenix, which is where I'm at now. And
nice.
Been here now, 8 or 9 years. So.
Yeah. So.
Nice. What about you, Pete?
How I came to Grumfoss? Or
yeah.
Where did I start?
What did you do after high school?
Oh, after high school.
I mean, we're going way back.
Way back. So I went to school, typical for a lot of my friends at the time. I didn't know what the hell I wanted to do, but I got a degree, and then I traveled a bit. And I come from a town, like I said, in the Finger Lakes, central New York, that's known for two things. It's the Women's Rights Hall of Fame, Katie Stanton and people like that, and Gould's Pumps.
Okay.
So the only thing I knew when I was finishing high school and college is I did not want to sell pumps.
Nice.
And so after a couple years of trying some different things, I got an opportunity. I wanted like a real job, and had some friends that got into sales with Gould's, and put my name in and they offered me a sales territory in Wisconsin. So equally crappy weather compared to Syracuse, so I thought it was a good fit. So I went to work for them, and Bell and Gossett for a little bit, sold some boilers, ended up getting to know some people at Grumfoss, and like Chris, a good opportunity came around, and I'd gotten to know the company a little bit, and was like, yeah, this is a good next step.
Yeah.
And it was that was 13 years ago, so
nice.
It's worked out very well.
Awesome. So, I think and it's kind of cool that y'all both kind of come together and working on this new distributed pumping project. Obviously a big focus of the booth this year, and for kind of Grumfoss going forward, this new distributed pumping deal. So can you give me a little bit of a background on how you got kind of involved with it and what distributed pumping is all about? We'll start with Pete.
Okay. Well, we tend to pioneer a lot of new technology in the industry, and what that really has been the last 15, 20 years is on the electronic side. There's only so much you can do to a pump.
Absolutely.
So we've been on the front end of we make our own motors, really pushing the edge of motor efficiency, integrate drives into those motors, have onboard controls. So like I said, it's been around a long time, and our one of our biggest innovations was a Magna 3, which came out about 10 or so years ago, and we've had a lot of good success with it. But I think people once they started to use it and get a feel for the pump and the technology, it's like, we can do more with this.
Sure.
And on the HVAC side of our business, a lot of the problems, let me step back. The pump tends to be looked at a lot of times as a problem point in the system. we get called in, you guys probably get called in. Well, actually, a couple quick tests, the pump's working just fine, but there are flow-related problems in the system, and a lot of that boils back to balancing.
Absolutely.
Right? So we, pumps in general need to be oversized, so we do these really big pumps, a lot of flow, a lot of pressure, and then we've got to knock that down at the places in the system we're going to use them, balancing valves. So as the pumps got smarter and had more capabilities, some people, a couple reps around the U.S. started to question, hey, maybe we could do this with a pump instead of a balancing valve, but nobody really went the distance and sort of, as a concept. We'd tell a design and consulting engineer about it, or tried something with a design build contractor, and they liked the idea, but we never really brought it to the end. And in 2018, I think it was, we had a couple guys from Grumfoss, Denmark, who came out to the field. I think they went, Singapore or a few other places in the world, because this was bubbling up all over the place. It wasn't just here. Visited a few customers here in the U.S., and there were some different thoughts as to how to do it. They sort of gathered all that data, went back to the drawing board, and just designed a chilled water system, one system, how's it going to work? And they took it to the end. And in theory, it was going to work. So then they found a university engineering school in Niam Polytechnic in Singapore, and they were looking for a better solution, trying to be really on the front edge of energy savings, particularly with their HVAC systems. And they had already had essentially a LEED Platinum building.
Right.
So they got a LEED Platinum building. They'd already upgraded their valves to pressure independent control valves. They were doing all the right things, and they'd made some improvements on the system, but they weren't getting the delta T that they wanted. They knew they were spending too much money. So they did an experiment with Grundfos Distributor Pumping, swapped out the PIC-Vs for the smart pumps, and it went from there. So that was the idea. It proved out. United States is a big market. I got sort of sent over to Denmark to hear about it. Okay, we'll make a plan, and we started talking to customers, and there was some interest. But we've been really, with the pandemic and everything, we've been planning a lot. In anticipation of this show. Really, getting, some visual aids for our customers, and, when talking to a lot of people today, it's going really well. So anyway, that was the whole long story.
No, but I mean, it's really cool that it's kind of this organic development from the smart pumps to the bigger solution, right? Like, how can these be used in a different way? And that's really slick. And I know we've worked closely with both of y'all on this, and it's something we're definitely excited to bring to the Houston market. And so, I mean, kind of, Chris, I know we've talked with you about it, but what's been your involvement in distributed pumping, and kind of what's your take on it high level?
Yeah, so I started with this back in early 2001. 2021.
You were way ahead.
I was way ahead. I was that far advanced.
It was in 8th grade, man, killing it with the distributed pumps.
I did. Kids would doodle, pyramids and, the little things. I was drawing distributed pumping back in the day. That's how advanced it was.
Visionary.
Nice.
So I started with this back then, and to me, when I first heard about it, I was like, okay, that's neat. It's cute. But then once I really understood it and I got into it, and I see this with a lot of people, once they truly get it and they understand it, it's like a light bulb. Like, you can just see it. Like, people go, oh my gosh, like, this changes everything the way we've been doing pumping, whether it's primary, secondary. Like, this is revolutionary on what we can do, because it solves so many problems, just like Pete was talking about. It solves a lot of the balancing, the low delta T problems. And I feel like a lot of times people, when they have these issues, the low delta T, the imbalanced system, high energy costs, when they go after those, they typically just go after the symptom. The symptom is like low delta T. We're not addressing the true problem. This addresses all those problems that I can almost assure you every commercial building has one of those issues in it. And they may not even realize it yet. And a lot of people think, well, that's just what I have to live with. That's the nature of HVAC pumping, whether it's chilled water or hot water. I just got to live with it. And then once I saw what the capability was, I'm like, this is going to change everything. And it got really exciting. It's really fun to talk about. I mean, I'm a pump nerd. Pete's a pump nerd. We love talking about this stuff, and a lot of people really they see it too. It's great.
No, I agree. I've had a similar conversations with people, and just kind of talking through the concept, and you can kind of see the wheels turning a little bit, and they're going, what about this? What about this? And then all of a sudden, like you said, it's like, wow, this makes a ton of sense.
And what's funny is we'll start talking about it, and then they are 5 steps ahead, and they go, wait.
Yeah.
This means that you can do this, and it's doing this. I'm like, yeah, that's exactly what it means.
Yep.
And they just, it tells itself. It teaches them everything.
So, we're talking about specifically the closed loops, right? The chill water and heating hot water loops, where typically you would have to, with the primary pump or maybe with the secondary pump, depending on how the design is, but you would have to generate enough head pressure to give those valves, the control valves or balancing valves, that pressure drop to be able to control the flow or attempt to control the flow at the different devices, fan coils, air handlers, things of that nature. So how is it that, explain the process, like what is the impact of changing out those flow balancing valves or the control valves to pumps? How does that kind of flip the system?
Basically, I like to think about it as like a demand-driven system.
Okay.
Right? So what generates the flow in any system is the pumps.
Yep.
Right? In the system you're talking about, a more traditional system, we over-generate for the system and then we knock down. Right? It's just the nature of how it has to work. In the distributed system, a pump is essentially a flow control device. Valves do not have a monopoly on flow control. So pumps, are perfectly suited for that. We put it out at the load. So if you take one particular air handler, the air handler has been sized already. We know what the load is. An engineer has looked at this building and said, okay, we're going to have this much heat gain, at the hottest day in the middle of summer. And I know what my chiller's size, my chillers should be. I'm going to break that down, to the individual, air handlers and spread that throughout my building. So they know right away what that flow rate is. That's never been the problem. The problem is the head pressure. How do you calculate that? There's a lot of rules of thumb in the industry, and which keeps driving it up and up and up, more and more and more oversized. With distributed pumping, what we're doing, we know specifically where we're drawing from. We know the pressure drop of the primary components in the terminal unit, the air handler itself, the pump itself, a check valve. That's it. And then we know the distance back to the bypass, which is our hydraulic connection point to the primary side of the system. And so we can really easily, especially with some tools that we've designed, design what that head loss is, come up with that number, get that head loss. We know what the flow rate is, and then that's it. We never, ever overpump the system. We give that air handler exactly the flow that it needs with only the pressure necessary. So not only does us get away from valves and, putting the brakes on, driving with the pedal to the metal and the brakes, to throttle, is that, we, by not overpressurizing the system all over the place, we're not affecting anything else. The problem with balancing is, in theory, you can do it. I've sat through the training classes and how you do it, and it's a ladder system. You start here and you build your way out, start back or build your way in. But any change you make at any point in that larger system, you've now affected your scheme for the whole thing. Each one of these these loads within a distributed pumping system is independent of the others.
Right.
It's decentralized command, or however you want to look at it. And they all act independently of the other, and they don't affect the other. So we're just never going to that level of over pumping the system. Yep. So and that alleviates a lot of the pains and the stuff that we've been talking about.
Yep. Yeah, it's constantly balanced, and that's one of the things that people seem to hone in on really quickly is the balancing. I mean, I know there's big numbers in energy savings and improved LT and other benefits, but the balancing is one of those things I feel like immediately people gravitate to, and they're like, wow, this is always going to be delivering the water where it needs to be.
Yeah.
So, Chris, so now we've taken the load, a lot of the load off the primary pumps and literally distributed out to all of the different places. So now you have those distributed pumps taking a lot of that head loss. What does that do to the primary pumps?
So our primary pumps, they are going to be sized for, traditionally primary pumps are sized for full friction loss for the entire system. What we're doing now is there's going to be a decoupler closer to those primary pumps to that mechanical room. And we're going to size that for the friction loss for that small loop through our chillers or boiler, through our decoupler and back to the pumps. So much smaller friction loss. It will still be sized for the full system flow. So if the whole building is calling for chilled water or hot water, it can handle all that flow. But because we're not having to do the full system friction loss, those are going to be a lot smaller, not just horsepower-wise, but also just space-wise. It gives you a lot more room in your mechanical room. We can use pumps that have ECM motors now because maybe we had to use 30, 40, 50 horsepower before. Well, now we don't have to. We can use smaller horsepower, gets us in that ECM range, much more efficient in that area.
Yeah, and that's huge, right? I mean, we've done a couple of calculations on existing systems, and it would cut the horsepower in half or more of the primary pumps.
Yeah, easily.
And that's huge.
Yeah.
So now you've got the smaller primary system, right? It's still controlling at the chiller, right? Making sure that we have minimum flow at the chiller. But how is the control of the control of the primary pumps happen, and then what's happening out at the distributed pumps?
Yeah, the good question, because we are controlling them a little bit different. So if you're already familiar with primary pumping or primary secondary pumping, we're really not that much different. And I often get the question is, well, if this is so great, why didn't we do it 10 years ago or 20 years ago? And honestly, we knew about this. Every manufacturer knows about distributed pumping. And we've been talking about it for decades. The reason why we do it today is because the controls have finally caught up, the technology, the cost point, it all makes sense now. That all those roads have now come to a point, and we can do this. So how we control primary pumps, they are first, their primary objective is chiller protection. So we're still going to run a differential pressure sensor across the chiller, wire that back to the controller. We'll maintain minimum flow across the chiller at all times. Then at that bypass or decoupler, we're going to have 4 temperature sensors. They're going to be about 4 to 6 pipe diameter away from that decoupler. And then those are also wired back to the controller. And depending on which temperature sensor, what we want to do is maintain a 0 degree difference on my primary side to my secondary side. So we want to make sure we got that 0 degree difference between my supply and my return water.
You want a 0 degree difference on either side of the bypass on the primary and a 0 degree difference on the secondary, right?
Yes.
But you're still maintaining, delta T across the primary and secondary, but it's the difference at either side of the bypass on either the primary or the
supply and return. I think that's the way to say it.
Right.
Because what that gives you is once those are matched up, then you have 0 flow across the bypass.
Right.
And if there is no flow across the bypass, that means that the primary skid is generating the precise flow that the secondary terminal units want to be using. So that's matched up. So you're essentially at that point you're optimized.
Okay.
Yeah.
So if you start seeing imbalances in the 2 sensors, say on the return side, then you're saying, okay, well the primary pumps are either over pumping or under pumping, and then you're able to ramp them up and down from there.
Yeah, and it's kind of hard to explain, but depending on which sensors are up or down, will determine that it will tell the controller we're pumping too fast, we need to pump more, there's more demand in the building. Because those secondary pumps, those distributed pumps, are sending back the water at a higher temperature because they've utilized that heat transfer.
Right.
And so once they trip that sensor sees that increased temperature. That's how the primary pumps know, oh, I've got demand, we should probably start speeding up and pull more through. I need to get that temperature sensor back down.
Right.
And so that's how we're helping to, the pumps are not connected electronically together, but they are hydronically, depending on the temperature and the flows that are going on.
Right. So, that's a pretty, again, keeping that system balanced all the time. So that's at the primary side, and you said they're kind of not electronically connected. So how are the distributed pumps being controlled, Pete?
The distributor pumps, it's really quite simple, and it really is aligned with how the control valve would have been in the first place.
Right.
So we're going to look at supply air temperature, so our outgoing air temperature from the air handler going into the air distribution system or the conditioned space, and based on that temperature, we're going to adjust pump speed. If it's warm in the space, we're going to speed it up and put more chill water through the heat exchanger. If it's cool, we're going to slow it down.
Right.
And that's it. And then like Chris said, hydraulically, that all is then interconnected with what's being done at the primary system. Those primary pumps are reacting. If the controls are set up right, the chiller's reacting, and you're only producing what you need.
Right. And so, you have that kind of one-to-one. You have a single pump to an air handler. So when the air handler turns on, it's going to enable the pump to run, right? And then it's getting that temperature signal back and controlling against it. So when it shuts off, you have that check valve on the outlet side. Hydraulically, so that if it does shut down, you're not getting the reverse flow, right?
Any of your other zones that might be operating aren't going to impact and push flow back through the air handler.
Right, and I guess that's kind of that difference between having the control valves versus having the pumps, right? The control valves can just or isolation valve just shut off and isolate the zone if they're using valves. Well, you can't. If you turn off the pump, it's not going to stop the flow coming back. So got to have that check valve on the discharge side. So
but the pump is not a flow inhibitor; it's a producer, and that's really what we're changing now. Before we were using components that were inhibiting flow and stopping it. Now we're putting something that's only generating. There is nothing to inhibit it other than that check valve to keep it basically the flow going in the correct direction.
Right, and we use that analogy all the time that you mentioned, Pete, of flooring the gas pedal and using your brake to regulate your speed.
Yeah, that's it.
And it sounds like almost sounds dumb when you say it like that. You're like, who would drive their car like that, right? Like nobody would do that. And so then you think, man, why do we do this in pump systems all the time?
Right. Well, and that's what we used to do think about domestic water pressure boosting. We would have a pump and feet away we put a PRV, pressure reducing valve, and knock it down. That's really what primary, secondary is when we're using control and balancing valves is a PRV.
Yep.
Yeah, the same idea. So we got away from that with domestic pressure boosting. We're now getting away from that with HVAC.
Yeah, and it is, again, it sounds so simple. So it's really cool to kind of see it working. And, we've got the working display here in the booth, but I know we've got some other kind of animations and other things that show all of this happening and what's going on in the system. So you kind of mentioned it a little bit already, Chris, but what are those parts and pieces, those pumps and kind of controls that have caught up that are allowing us to do this? Like, what are the different, there's been kind of this shift, or what we talked with Sherzad about the shift from products to solutions with Grumfoss. So, like, what are the products that are making up this solution?
I'd say, the one thing that jumps out is the Magna 3, because it has built in everything. When we ship the Magna 3, we don't ship it with something specific for distributed pumping. We have no idea what application it's going into, but it has everything on it to do distributed pumping already. Right. It has we can add it into your building management system with the SIM card. It has the integrated temperature and differential pressure sensor already built in. We set it to a constant temperature mode. Normally we would be using constant temperature for the water, but here we're going to be using the supply air duct temperature. Right. So we set the supply air duct temperature, and that's about it. Everything else, it basically runs itself. The algorithms, what am I thinking of? The sequence of operations is all built in. It's all there now. And so that makes it so much easier. Then I think when we get to the controller, that does have the special algorithm for distributed pumping.
On the primary side.
On the primary side, yeah.
But it's still a variation of the CU352 controller that we're used to from the Hydro MPC. So, it's basically just a variation of the Hydro MPC, right?
Yeah, exactly. And traditionally we do differential pressure control, and this is just temperature control, really is all it is.
With a little bit of differential pressure thrown in there.
Yeah.
Well, that's a good point. Like, I always point this out, is before we were pumping based on pressure in our mechanical room. We have a differential pressure we're trying to maintain. And then we hope that pressure translates to the correct pressure at my air handler, which we hope translates to the correct water temperature, which we hope translates to the correct air transfer to air. Right. Well, what we're doing now is we're bypassing all of that. We're going straight to the air temperature. The final result is we want a comfortable space at a certain set point. Let's operate the pumps on that exact set point. Let's skip the pressure.
Sure.
We don't need that. Let's just go right to what we need and stop losing all that lost in translation points.
And so we've got the Magna 3s distributed out, right, and either controlled to the air temperature on an air handler. If we've got smaller kind of bank of fan coil units like we show over there, then we maybe are using proportional pressure or differential pressure there. Yeah. And then in the primary side, now we've said, you mentioned earlier, we kind of pull back from the larger pumps and potentially even use like the TPE3, like the smaller, super efficient, most efficient pump in the whole Hydraulic Institute catalog, right? Yeah. At the primary pumps, or even larger with the NBSEs or the CRXLs. So very flexible with all of that. But again, I think it kind of goes back to that point of all of these are products already within the Grumfoss kind of catalog, but just being applied specifically in a way where delivering the best air temperature, like you said.
Well, I think that's funny you say it like that, because that's kind of how I've seen it. The products we have here today with the primary, whether it's TPE3 or Magna 3, they're not new products. We've had them for years. Yet this is being displayed as a new product, and it's generating a whole lot of buzz. And it's a solution. It's a new solution. It's not new products. They're products that we've had around for a long time.
Yeah, and I think that also speaks to the reliability of the system overall, right?
Exactly.
I mean, the TPE3, the Magna 3, CRXL, CR, all of those rock solid products. And so I think initially people might look at this and go, man, this is a big leap to move to a system like this. But, and you know, I've had people initially kind of recoil and go, oh, but now I got to maintain all these pumps.
Yeah.
And so how often does a Magna 3 really require any maintenance, right? Like is there any difference between having all of those distributed valves, right? Like, are they that much more reliable or less of a mechanical or electronic concern than a pump would be? So I don't see it as that big of a jump, right, from that standpoint.
Yep.
But I think really what gets people's minds rolling in this or getting them excited are the additional benefits. You know, I think one of the things that jumps out initially is that reduction in the pumping energy, right? Like, because now we've reduced the need. We're only pumping what is being used. But what are some of those other benefits that come out of the distributed pumping system?
Well, I think one thing, and you were just sort of hitting on it, and, you know, people, something different, they cringe or they recoil a little bit because it's going to be, you know, just different. And we call this in our literature, it's a paradigm shift, which is, you know, real grand, you know, big sort of word. But it is. It's truly, you know, a big shift in how you do it. But I think the beauty of it all, and you and I don't know, several months ago got into this conversation, is what it is, though, is even though it's big and it's different and there's savings to be had, we're simplifying the system.
Yes.
We're pulling a tremendous amount of complexity out of the design process, out of the operation, you know, long term, you know, balancing, you know, what happens when the system fouls, what happens when something changes in the system. All of that's gone. This is just a simplification that, you know, delivers a better performance, you know, less energy. And so to answer your question, you know, besides that reduction in pump energy, we are having a significantly positive impact on the chiller performance as well. Yeah. And what we've seen is, and these are just, you know, we're just still at the front end of this whole thing, but we're realizing 30-40% improvement on the Delta T the minute you turn on those pumps.
Wow.
Like you look at a baseline for an old system, swap out, you know, take out valves, put in pumps. At the speed at which those pumps operate and sort of dial the load in, minimize the flow across the bypass, you're now seeing return water temperatures 3, 4, 5 degrees back to the chiller right away. And that everybody, I think, that's been around a chiller plant, optimized, you know, or operates a chiller plant, knows that translates into dollars. The first case is one of the only quantifiable ones we have in regard. We had good data on the chiller side, is we reduced the chiller energy, you know, the annual electrical use by 2.5%, or 2.6%, which, you know, big numbers on the pumps, you know, 2.5%, but when you look at what a chiller uses on an annual basis, particularly in a warm climate like Houston or Singapore, or whatever it is, it's big money. You know, that's where the ROI comes from.
Well, and that's a tough one to start with too, right? Because that was a lead, the equivalent of a very high level lead building. So it was already super efficient.
Yep.
And you improved it even more. So I think the opportunity in a typical mechanical room is going to be a lot greater. Yeah. But the higher Delta T, I think, also goes back to what you were talking about, Chris, with the increased benefit in the space, right? Like the comfort, like that Delta T speaks to better heat transfer out into the system, right?
Yeah. Well, think about the space. On a traditional HVAC pump, we're usually looking at an end suction, usually several feet long. Takes up. When we can get that down to a TPE3, that's the size of a table lamp that you have in your living room. That's how big the pumps we're talking about here. It's not a small change. It's a big change in just the footprint alone. And a lot of times I hear people go, wait, I'm taking out valves and I'm putting in a mechanical pump and I'm going to have these all over my building. That's a maintenance nightmare. But Magna 3, there's no maintenance. There's nothing to grease. There's nothing to change, no seals. There is zero maintenance for these. A valve does still require maintenance. There is usually a cartridge, something that needs to be a filter, or something that needs to be maintained over time. That often doesn't get done because there's a lot bigger things that need to get done. So this is truly less maintenance overall with this type of a system.
Right. No, I would agree. And I've had that same reaction for sure. But you know, we're obviously very comfortable with the Grumfoss pumps and have seen how reliable all of them are. So we have no concerns there.
Good.
But the you know, I think the other thing that to consider on the benefits on this is like that what their tenants or guests or patients, whatever, is using the building is going to have a better comfort in the building, right?
Yeah. There's a lot of things that it helps solve. Is we're going to have better comfort in the building, because a lot of times what ends up happening is, I see this all the time, occupants complain. So somebody goes in, they go, well, we need more chilled fluid. So they open up a valve. Well, immediately the system is now out of balance from the day it was started. So you may be getting more chilled fluid there, but that means you're probably robbing it from somewhere else. So they go to that space and they have to adjust that valve. And you can start to see the pattern that starts to happen is it becomes a mess of now everything's out of balance. You got some spaces that are getting too much, too little, and that solves all that. This fixes the occupancy comfort, because again, we're operating to the exact temperature that we want in the space, not some mystical set pressure that doesn't necessarily translate to 71 degree or 72 degree air in the space. Nobody cares and says it's a little bit hot in here, but we're getting the right head pressures in the mechanical room, so I think it's okay. Nobody ever says that. They say no. It's too hot.
Exactly. No, I agree with that, and so I think this definitely can be applied to existing buildings, right? But there's a little bit, I guess, some timing that needs to happen just because the pressures are different. In distributed pumping, kind of inverted from typical primary secondary pumping. So let's I'd maybe talk new construction for a minute, new design, ground up building. What would the design process look like? Somebody wants to go distributed pumping. How can Grumfoss help in that?
Yep.
Pete, you got that one?
Yeah, no, that's good. Really, if whether you're starting from scratch or you've already got a design, and you want to convert it, we just have to get into the sizing of the pumps, really is all. And how we are going to do that is we're going to sort of do that. We're going to help out with that. So we've got a team of applications engineers. We've developed a system design tool that we can design any mechanical system, really. It doesn't have to be distributed pumping. We do variable primary system, primary, secondary. But of course, the development of it came with distributed pumping, because we knew, not that it's hard, not that people wouldn't be able to figure out how to, get what the head requirement would be for these pumps, but it's just different than what you're normally doing. So do you want to teach people how to do that, or you just want to give them a tool that does it for them? And that was a no-brainer. So we've got that. Right now, how we're going to do it is we're doing those designs. We will be, over the course of this year, going out training guys like yourselves. We'll get you guys up to speed on it, and then as you encounter customers of yours that would rather self-serve, they need to do it themselves versus hand it over to us, we will give them a license to the software and let them rip.
Nice.
So it's really just about, if you've got a system designed, send over your drawings, send over your loads. We'll convert it over to a distributed pumping system. We'll give you an energy report, show you some of the differences. If you haven't done the design work, then just set up a Teams call or something, and we'll ask you the questions, and we'll get started on it.
Nice. And so, it's the overall kind of design shift on the front end isn't going to be that massively different. The piping not necessarily changing.
Yep.
Right. The components outside of swapping the valves for the pumps, outside of that, the rest of the components in the closed loop are basically the same, right?
They're the same. And that's one of the nice things about it, because there's been some different strategies out there in the past, but the whole system changes. And you start doing things, where your pumps affect other pumps, and there are types of systems that are actually adding complexity to it. And that's where I think the crew that sort of came up with this design for Grumfoss has really thought it out, and it's the reduction in complexity that really makes the difference. So,
and like I said, if I think there's also a massive opportunity in existing buildings to move to distributed pumping, especially you look out at the goals related to the Paris Climate Agreement, reducing the carbon emissions in a building, or if it's related to corporate ESG measures or goals that they want to meet. A lot of the buildings that 70-80% of these buildings that are going to exist in 2050 have already been built, right? So this is a huge opportunity to reduce that energy savings or energy consumption in the building. Is just because you have more pressure on the return side now instead of the supply, can't necessarily just kind of put the pumps in and run a mixed environment, right?
Right. Yeah, that's kind of all or nothing. We either have to go all distributed pumping or stick with the traditional route. And the great thing is we've got a lot of great tools for this. We've got a lot of white papers, like Pete was talking about, was the software for sizing this, brochures, videos. We also have a tool that we can analyze an existing building, and we really just need basic layout of the building, air handler information, chiller information, something we can calculate all the friction loss. And we'll put together an ROI and say, okay, if you were to convert, this is how much it would cost, this is what your pumps would look like, this is how much electrical savings you could expect. And we've done this enough that we're very good at understanding what that would look like. And that's why it works great. Just like you said, a lot of the buildings that are going to need this are already built. So it's a little too late on those, but we can still retrofit them later.
Right.
And in new construction, that works great for new. Obviously, it's much easier when you start with this at the beginning.
Yeah.
But a lot of the projects we're doing right now, we've got several going on right now that are all retrofits. And it is possible, and it works really well. Especially because they see, I have low delta T. I've got balancing problems. And each building, every owner I talk about, they always have a little bit different reason, but it's all the same as, I have this problem. I don't know what else to do. I have spent so much time and money trying to do this. I need something that works.
Right.
And this works because, again, they were going after the symptom instead of the true problem.
Right. Yeah, and we're absolutely going to be there to help in that process. You know, we can help go to the existing sites, get that information, work with y'all to do the design, and then on the new construction, obviously working with the mechanical designers to help lay that out. But, you know, I think it's a huge opportunity to not only have that energy savings, but to solve all these other balancing and comfort issues with the chilled water and heating hot water systems in a way that's not, like you said, kind of starting from scratch or complicating the system.
Right. Absolutely.
So, awesome. Well, any other thoughts that y'all have on distributed pumping or any other kind of things that are going to come out of this, or this kind of shift from products to solutions with Grumfoss? Any other things that y'all would like to share?
Not off the top of my head. I mean, one of the cool things about distributed pumping is it's, you know, sort of an extension of what our mindset's been for the last several years.
Sure.
You know, we make pumps. We're a pump manufacturer, but we get asked to do more, you know, and we have the motor efficiency we talked about, the controls, the smart pumps, but then it's also the skidded systems. You know, construction industry's tapped, you know, labor's tough, you know, so we've been focusing on systems for a long time now. It's become a huge part of our business. So we tackled, you know, that mechanical room, solved a lot of problems for engineers looking for space savings and wanting to make sure, you know, their design, what they intended to happen is, you know, delivered in the construction. And then contractors who, you know, are up against tough timelines and, like I said, struggle with, you know, maybe labor or, you know, juggling multiple projects. We've helped them, you know, in those situations. And all distributed pumping is just sort of, you know, solving some problems farther out in the system. You know, so you know, that primary skid is still, it's just one of our skids. That's what we've been talking about for a long time. So it's just very aligned with where we, you know, as a manufacturer are, and our sales teams are, and our partners are, and, you know, what they're offering to the market.
Nice.
Yeah, going along with what Pete said, we're really getting into more systems. So before we made pumps, we were just worried about our pumps. And air handler, he was worried about his air handlers. And chiller, he just worried about his chiller. Like, we never really cared what the other one was doing as long as we were giving them what they needed. And this is a shift. This is now saying we're going to make the chiller operate. We're going to help the chiller operate more efficiently. We're going to help the air handlers work better. We're going to help condition the space. We're going to make this entire system, all those major components work together, actually work together as they were designed, as efficiently as designed. I mean, the owner's paying an engineer to design a system, and he's come up with a delta T, and he's picked these products for a reason, to get the most efficiency out of them. And unfortunately, when they get installed, that all kind of goes away. What we're trying to do now is, you paid for this service, let's get all we can out of the services that you paid for. Let's get all the value out of it. Let's make everything work together.
Yeah. No, it's great. And like I said, it's something we're really excited about. And I know in Houston, we're lucky enough to have the new Grumfoss headquarters facilities there that has distributed pumping set up, you know, beautiful, huge mechanical room, and you know, just awesome building in general. So you know, hopefully as we get out of the kind of the pandemic here and into a more normal environment, we'll be able to go out there and do some customer trips out there and be able to actually show this in person and not just in theory or on a demo wall here. But it is we do have a nice installation close to Houston that we can show off. So we're excited about that.
Yeah. Exactly.
Well, awesome, gentlemen. Well, I appreciate you coming on the show and talking with us about distributed pumping and Grumfoss in general. Any final thoughts, words of wisdom for our listeners today?
No, I just think I think Pete actually talked about this a little bit. Is the industry's changing? There's definitely a skills gap. There's just not as much knowledge as was out there, and I feel like that's what we're doing. We're helping to fill that gap with a lot of this stuff. But I guess I just encourage people to gather as many opportunities as you can, whether it's at a show like this, at your local ASHRAE, ASHI, whatever organization you've got.
Yep.
There's just a lot of knowledge out there, a lot of opportunities. Just use all those opportunities, network, and don't just network to, advance yourself. Like, help other people out.
Yep.
Just because you meet somebody, they may not immediately help you, but you might be able to connect them with somebody else.
Absolutely.
And that just makes our industry so much better. I meet so many wonderful people in ways that I never even would have imagined. And I just think there's a lot of great opportunities with this stuff.
Well, Pete, Chris, really enjoyed having you guys on today. And again, thank you for sharing your time and letting us take over a little bit of the Grumfoss booth here. But definitely always enjoy talking with y'all.
You too. Thanks
Tim.
for the opportunity.
Awesome. Also want to thank everyone for watching and listening, and look forward to seeing you on the next episode of Building Value.